Hi guys, my name is Shubhang, chemistry master teacher at Vedantu, and I am back to discuss reaction mechanism with you guys. So we covered 2 sessions of reaction mechanism. Now this is the third and the last session of reaction mechanism in the series. Why are these 3 reactions, guys? And we have tried to discuss extremely important concepts with respect to JEE Advanced, concepts where we generally commit lot of mistakes in the exam, concepts which are not very clear to us. We did not pay too much attention on reagents and their uses, that I'm sure you can figure out. But the questions where we get stuck again and again, where SN1, where SN2, the mechanism part of it, that is what we concentrated in the first 2 classes. So I'm back today for discussing more and more questions with you, and I have some amazing questions and concepts ka collection for you today. Okay, so sit back, relax, take a paper and pen and start solving. Here's the very first question for us, guys. So this is the very first question, guys. The question says we have aryl diazonium ArN2 plus, right? So that's your aryl diazonium salt. He says if you react this with Y minus, we know that substitution reaction takes place and N2 goes away and Y minus comes into the place of N2, nucleophilic substitution reaction in aromatic compounds. Where did we got diazonium? That's not part of the question. What is part of the question here is the mechanism of what is happening here. So in general in our classes or when we study, we don't cover the mechanism of this part, right? So let's go into it and let's discuss what is happening. So this looks like a direct substitution reaction, but when we talk about experimental observations, what is obtained is it's a 2-step reaction. It is observed that it is a 2-step reaction. In the first step, diazonium ka N2 plus leaves away as N2. If you remember, N2 is a very good leaving group. It converts into a neutral system and can go out on its own. That is what happens here. In the first step, in the slow step, in the RDS step, we get a phenyl carbocation formed. This is your slow step, this is your RDS step. Phenyl carbocations are generally very unstable, right? We don't form them, but there are practical evidences of phenyl carbocation forming in this mechanism. So indeed it's a 2-step mechanism. In the first step, which is your slow step, we do get a phenyl carbocation formed, and in the next step your phenyl carbocation reacts with the Y minus nucleophile that we are adding. Simple combination reaction takes place and Y gets attached. This is your step 2. So first step में we are creating a reaction intermediate, second step में we are using up the reaction intermediate. So definitely the first step has to be the slowest step, the RDS step. Chalo, now let's answer the question once we know the mechanism. So first point of the mechanism, the rate law is given by K into ArN2 plus. How do we write rate expressions? We write rate expressions from the RDS step. In the RDS step, that is your first step, what is used up? In the RDS step, ArN2 plus is your reactant, no other reactant is present. Each step of a mechanism is always an elementary step, and therefore we say that your step 1, which is the RDS, is first order with respect to ArN2 plus. That means 2 things. ArN2 plus the concentration doubles, the rate doubles. That also means Y minus is not involved in the rate expression. Y minus ka change in concentration does not change the rate of reaction at all. Why? Because Y minus is involved in your second step, that is your fast step, not the slow one. So first option is definitely correct. Rate is independent of Y minus, we just saw, that is also correct. As I told you that there are practical evidences in this reaction of a phenyl carbocation getting formed, and hence the third is also correct, product of step 1. Now decomposition of diazonium cation is reversible. In general, if you look at this overall reaction, you would think that this is not a reversible reaction because N2 is a very good leaving group. Agreed. But do we look at the overall reaction or do we look at the RDS when we talk about the mechanism? We look at first the RDS. If we are not able to answer or if it is too complicated from the RDS, then we go at overall reaction. Correct? So let's take our concentration back to RDS. In the RDS step, we do have a good leaving group N2, but we are making a very unstable reaction intermediate. We are making phenyl carbocation here. Okay, and that is the reason your first step is reversible in nature, because very unstable, very poor stability intermediate is getting formed in the first step. It is found that first step is indeed reversible in nature. Second step will be very fast because we are using up a reaction intermediate. So fourth is also correct. So very interesting question. We definitely learned something new from this. What is the mechanism of substitution in a diazonium salt? It's a two-step mechanism. Step 1 involves the formation of a phenyl carbocation, as you can see here. And step 1 is also reversible in nature. And step 2 involves the reaction of the phenyl carbocation with a Y- with a nucleophile. Simple. Very interesting, very challenging question with respect to JEE Advanced. Why challenging? Because we know this, we don't know this theory at all. So if we don't know this theory at all, we'll end up marking all the options incorrect. We'll say that both of them are involved in a single step. So both concentration should be valid. So you'll mark A and B wrong, first and second wrong. Then obviously you will say कि यार who will form phenyl carbocation? नहीं होना चाहिए. So you'll mark 3 also wrong. Then last, reversibility to not possible. So you'll mark all of them wrong, whereas all of them are correct. ठीक? So good question guys, please do revise this again and again. It's a very important mechanism, I believe, from JEE Advanced 2023 perspective. Shall we? Let's move ahead then. Now, the next question says sum of alpha hydrogen in major product of few given reactions. Such type of questions are also hot favorite of JEE Advanced paper setters. Why? One, it allows them to check the dehydration mechanism, one of the very important mechanisms, because you have to form a carbocation, you have to rearrange. Then the second part is identifying correct number of alpha hydrogens. Okay, so dehydration, correct product, and identification of correct number of alpha hydrogen both becomes very crucial in solving such type of questions. So let's approach them one by one. What will be the product in the first case? So if we talk about the first case, H plus is present here. Definitely we will get a carbocation. What kind of carbocation? OH minus goes away as water and we get a carbocation here. This carbocation will surely undergo migration to become more stable. Now, in general, positive charge which is outside a 6-member ring cannot come inside a 6-member ring, but such cases, such direct simple case mate is possible. When you have 6-member ring and outside a methyl with a positive, nothing else is attached to the ring, nothing else is attached to the methyl, only then the positive charge can come directly inside the ring. So this gets formed and finally converts to a alkene. Now for this alkene, how many alpha hydrogens do we see? This is one alpha position, this is one alpha dash position. There are 2 hydrogens here, 2 hydrogens here. So 4 alpha hydrogen are present in compound number A. Let's go for compound number B. OH gets removed as water, isn't it? And you get a positive charge here. Again, positive charge will try to migrate and reach the most stable position. That is this. Sorry, this will be like this. Why did it migrate? Right now it has 2 alpha hydrogens here, 1 alpha hydrogen here, total 3 alpha hydrogen. How many alpha hydrogens do we see here? 1, 2, 3, 4 and 5. 5 alpha hydrogens, therefore it will definitely migrate. Heat is given, so therefore elimination will also take place. What will be the product after elimination? ZF alkene is obtained as a product after elimination. So we get pi bond in the center. 2 alpha hydrogens here, 2 alpha hydrogens here, 2 here, 2 here. Therefore we have 8 alpha hydrogens in this compound. ठीक, 8 alpha hydrogens as a product of your pKs. Now let's talk about the next one, that is your C. This is your positive charge forming. Will it rearrange? Yes, number of alpha hydrogen is again increasing, so it will definitely rearrange. Here you have 4 alpha hydrogen, here you have 2 alpha hydrogen. Will this further migrate? This may further migrate. Let's migrate it and make it more stable carbocation by hydride shift. 2 to 4 to 6, now it has 6 alpha hydrogen. So definitely from 2 alpha hydrogen it migrated to 4 alpha hydrogen, from 4 it gives 6, and now we will form stable alkene, that is ZF alkene, like this. 2 alpha hydrogens here, 2 alpha hydrogens here, 3 alpha hydrogens here, so 7 alpha hydrogen overall are present in this. Here your answer is 7. ठीक, last but not the least, direct carbocation formed, no rearrangement, nothing, because it is the most stable system. It has already most number of alpha hydrogen, and this will give you your alkene here itself at the same position. So 3, 3, 6 and 4 here, 10 alpha hydrogens in total. You got the answer as 10. So 4 plus 8 is 12, 12 plus 7 is 19, and 19 plus 10 is 29. Okay, so this is a challenging question, yes, involves lot of solving, yes, but overall it is not difficult. I'll repeat what we did. Compound number A is done here. We first make carbocation, then we rearrange the carbocation to a more stable position. Finally, we make ZF alkene. This ZF alkene has 4 alpha hydrogens as marked in the question, as marked in the solution. Compound B may we make a positive charge here, it rearranges to give a more stable carbocation, then it gives you ZF alkene as the product. You have 8 alpha hydrogens here as present in the compound. Next, the third one, we made a positive charge, we rearranged it twice so that it could reach the most stable position, and then we made alkene. This alkene has how many alpha hydrogen? It has 7 alpha hydrogens. If you make alkene inside, how many alpha hydrogens do you get? If you make alkene by chance inside, then you land up with 2 to 4 to 6 alpha hydrogens, so we will not make this. Last but not the least, decays carbocation formed then and there, direct ZF alkene 10 alpha hydrogen. Total 4 plus 6 12, 4 plus 8 12, 12 plus 7 19, 19 and 10 29. So that's 29 alpha hydrogens in this question. Okay, they are saying 32. Let me check. Oh yes. Here it looks like कि A में we should not have A वाले case में this is incorrect product. I'll just quickly correct it. I made a mistake. Just a minor typing mistake. ZF alkene will be the one that has more number of alpha hydrogens. So this is the answer. 3, 2 and 2. 7, not 4. This also has 7. So now our answer is fine, now our solution is fine, that's 32. Okay, chalo. Let's go ahead, let's solve the next question. Wow, looks very complicated. We have two diol systems with us and concentrated H2SO4 heat. Okay, what is obtained in the above reaction? Cool. So when we have diols and we have acid, what mechanism comes to mind? When we have diols and when we have acid, pinacol-pinacolone type rearrangement comes to mind. Correct? So let's take one compound at a time and solve. First, I'm looking at this one. I'm calling this as compound A. Now, in compound A, I have two positions where OH can accept water and give me carbocation. Okay? Suppose the left one took a OH, took a H plus and gave a carbocation at the left carbon. So what do we get? We get this. Let's say the same reaction took place at the right carbon. The same reaction took place at the right carbon. So what are we expecting? We are then expecting a positive charge. Oops. We are expecting a positive charge on the right carbon. Rest all of it remains as it is. Ethyl. The very first step always in pinacol-pinacolone rearrangement is to make the right carbocation, to make the correct carbocation. So we made both the carbocations. Now the one which is more stable is formed first. Out of the two carbocations, which one do you see as more stable? Obviously this is more stable, this is not, due to resonance with two benzene rings. So always more stable carbocation will be formed as the first step in pinacol-pinacolone rearrangement. Now, positive charge will migrate to the nearby position, right? So that it can resonate with oxygen. So ethyl group leaves. Ethyl group migrates. Suppose I take the above ethyl group to migrate. So what will we get? We have two pH already present and one ethyl migrated. We know the next steps. Lone pair goes here and the compound loses NH plus to give us the final product. So this is your final product for the compound A. I repeat, we are given two compounds. We have to do pinacol-pinacolone type rearrangement. We have to make carbocation and then rearrange in these cases. We approach one compound at a time. We don't take both of them together. In the first compound, first I checked where can I make carbocation. I can make carbocation on the left, I can make carbocation on the right. Whenever we make carbocation non-rearranged, first carbocation formed should be more stable if we have a choice. So here because we have a choice, we end up making a more stable carbocation, that is the right one because of resonance. Then we rearrange it, we migrate it, we do alkyl shift. Ethyl group migrates from the nearby position, giving rise to a carbonyl as a product. The whole driving force in this reaction is being able to form carbonyl compound as a product. Now let's continue here on our compound number B then. So if you notice, there is similarity in compound A and B. The only thing that is changing is the nature of this group. Rest everything remains the same. Let's go ahead with compound B. I'll change the slide. Oh cool, it's given here. So if we talk about compound B, this is your case. Compound B may also, we will form the carbocation on the right. Why are we forming carbocation on the right? Because of more stability, because of more resonance with benzene rings. Just like in the previous compound, ethyl migrated, here methyl will migrate. So methyl migrates from this position to the nearby position. What do we get? We get carbocation. We get carbocation. This lone pair resonates with the carbocation and we have our final product. There is one more reason why this question is given, or why this question was asked as a mixture of two reactants. The reason why this question was given and asked as a mixture of two reactants was to check whether you know or not that pinacol-pinacolone rearrangement is intramolecular in nature. Pinacol-pinacolone rearrangement is intramolecular in nature. It happens inside the molecule itself. So when we are making carbocation at this position, only the group present in the same compound can migrate. When we made carbocation at this position, only the group present in the same compound can migrate. This is intramolecular reaction, not intermolecular. Okay? Although we claim that whenever a carbocation is formed, any nucleophile can attack, I agree. I am still maintaining that statement. But carbocation is formed, rearrangement is always intramolecular. So we demand rearrangement. After rearrangement, due to resonance, automatically C double bond O got formed. So we didn't go for attack of nucleophile. We rearranged the carbocation and internal resonance, internal back bonding gave us a stable product. Good question overall, guys. Let's go ahead. Wow. Scheme 1 and 2 describe the conversion of P to Q and R to S respectively. Okay. Scheme 3 describes the synthesis of T from Q and S. Okay, so that means this is S. The total number of bromine atoms in a molecule of T is. Oh, then look, it looks like simple one. Chalo, let's start. First, we'll start with making Q. Okay. So we have aniline being given to us, and we are reacting aniline with bromine excess and water. When we are reacting aniline or phenol with bromine and aqueous medium, because of highly activated nature of the ring, tribromination takes place. When we have bromine and water present and we use whether aniline, whether phenol, tribromination takes place because the ring gets activated in aqueous medium. Next, NaNO2HCl, we know that aniline part, this NH2 part will convert to N2 plus. KCN cyanide se we understand that N2 plus wala part will get substituted with cyanide. So let me write the direct product after the first two steps. I'm sure you have mugged up by now the first two steps. NH2 ka reaction with NaNO2HCl at 0 to 5 degrees Celsius or in an aromatic compound gives us diazonium. Diazonium pe we are conducting substitution, Sandmeyer reactions. Thick. Next is H3O plus. So what do you get by hydrolysis of cyanide? When we hydrolyze a cyanide, cyanide gets converted to CO2H. What happens when you react a CO2H group with SOCl2? You get COCl. So I am writing the product here directly that instead of cyanide here, what do we expect? Instead of cyanide here, we expect C double bond O Cl. Cyanide gets hydrolyzed, and after hydrolysis, SOCl2 say substitution takes place. Instead of OH, we have Cl. So this is my compound, that is Q. Very important, we have to react in the last step Q and R together. So please remember. Now next, scheme 2, benzene ka reaction with oleum. What is oleum? Oleum is fuming H2SO4, that's H2S2O7. What does H2S2O7 does with benzene ring? Concentrated H2SO4 या फिर H2S2O7, they all make the benzene ring undergo sulfonation. So benzene pe SO3H is attached, that is your first step. NaOH heat. NaOH heat से what do we do? If only NaOH is a base, I agree my compound is an acidic H, but then nothing seems to make sense later. If I am using NaOH heat in the second step, why would I add H plus in the third step? If I am using NaOH heat just to neutralize this SO3H group, why would I use H plus in the next step? So that is not the purpose of NaOH heat here, to convert this SO3H into base. The purpose here is epso substitution. The purpose here is desulfonation, and SO3H group simply goes away. So NaOH heat followed by acidification. NaOH heat followed by acidification leads to desulfonation happening on the benzene ring. Not just that, because we are not using water, we are using NaOH, this would actually form phenol as a product. I'll repeat this step. When we are conducting NaOH and heat, desulfonation, epso substitution takes place, we get phenoxide ion. This phenoxide ion ko we are putting in H plus medium or acidic medium to convert it into phenol. This is your compound S. Sorry, this is not S, my bad. Now, what is the next step given, guys? Phenol pe we are reacting bromine in CH2. Now we are not reacting bromine in water, we are reacting bromine in carbon disulfide. So monobromination takes place. Phenol wala OH is a plus M as well as minus I group. So OH being a plus M group will push the incoming bromine electrophile at ortho and para position. Because it is minus I also, it is withdrawing also, I would like to put it as far as possible, and therefore we will put it at para position. So incoming bromine is put where? Is put at para position. This is finally your compound R. This is finally your compound R. This is S. So we have two compounds here with us. We have finally this compound as Q, and we got this compound in S. What does the question tell us? The question tells us S ko react with basic medium and then react with Q. When I react S with basic medium, the OH has an acidic H, so that converts to O minus. And now he is saying react it with Q. So this is a nucleophile or a nucleophilic center, as you see. Here in COCl we have a strong del plus at the carbon here. Therefore your O minus attacks that carbonyl compound. Okay? So what is the product expected? I am writing it in horizontal manner just to write it in a clean way, nothing else. So this is your 3Br that were already given in Q compound. Yahan pe you have a C double bond O, and instead of Cl now you have this oxygen which has attacked your ring. That means you have a benzene and you have a Br. This full big compound is your final product, that's R. Question was fairly simple, but there were lots and lots of chances of getting lost in the question, giving incorrect answer. First step was fairly simple, using bromine excess to give a tribromo product. Second step was also fairly simple, NaNH2 will convert this into N2+. It is after this step where we start making mistake. If you don't realize that water is given to convert cyanide to acid, if you don't realize SOCl converts acid to acid chloride, we will not be able to conduct the last step. Also, there is another very important position of mistake, this part. Here if you just conduct simple epso substitution, that is just remove away SO3H, you don't bring in OH, then you will have benzene here, not phenol. Benzene pe when you make it react bromine CH2, you will get one bromine in benzene, but then what will you do? How will you react the final S and Q together? You get stuck. So it's very important to understand this step here, NaOH heat followed by H plus, SO3H ki jagah you'll have OH into the picture. Interesting question, isn't it? This was a previous year JEE Advanced question. Overall not a difficult one, but very interesting. Chalo, let's go ahead. Now, compound A is something which reacts with PBr3, magnesium, lots of unknown. Oh, this is known. 3,4-dimethyl-3-hexanol. So 1, 2, 3, 4, 5, 6. This is your third position, let's say hexanol. Third pe you have methyl, fourth pe you have methyl. So this is my product that they are forming. Okay, this is forming after H3O plus, and Grignard reagent is reacting with a compound B to give you D. He is asking what is A. Cool. Now, from a very basic idea, how to approach these questions. Lots of unknown. How do I start with each and every option? It will take a lot of time. Carbon counting method. If you notice, we are not adding any carbons in these three steps. So whatever carbon that you are getting in the final compound is coming right from A. A को we convert into Grignard, A को we convert into B, and then we react them together. So how many carbons do we see here? 6 into 2, 8 carbons. Your reactant A should definitely have 4 carbons. Right? Tabhi to 4 plus 4 will give you 8. So let's try and eliminate anything that does not have 4 carbon. D option 1, 2, 3, 4, 5. This has 5 carbons. I wouldn't want D to be my answer. C option 1, 2, 3, 4, 5. Again 5 carbons. I wouldn't want this to be my answer. Rest A and B have 4 carbons each. Okay? Now let's try and start solving the question. Let's assume कि this is your compound A. This one is your compound A. So what do you get after solving? We have 2-butanol with us. 2-butanol का PBr3 and magnesium के साथ we'll get MgBr, isn't it? OH gets converted to Br and then magnesium reacts with it, converting it into Grignard. Now, when you oxidize it using sodium dichromate, what do you get? You get your ketone here. Grignard ka reaction with a ketone, addition reaction takes place, isn't it? Grignard ka reaction with a ketone, addition reaction takes place. We can write Grignard like this. And then the negative charge attacks your carbonyl. So what do we get? This was your O minus, and this is your 4 carbon system that attached or that attacked. This was D, finally H3O plus. Finally H3O plus, you got your product. Does it match with our compound? That we'll have to check by IUPAC naming it properly. OH is your principal functional group, longest running carbon chain. So this becomes your numbering ka system. And yes, it does match. It's the same thing, 3,4-dimethyl hexane 3-ol. Understood the idea, guys? It was just not possible to solve this question by checking each and every option. It will take a lot of time. So what did we said? We said that the product contains 8 carbons. This comes from 2 compounds made from the same reactant. So the 2 compounds each have to have 4 carbon each. That means A also has to have 4 carbons. So C and D option eliminated. When C and D option eliminated, then I started solving using options. I started solving with A. So first step में we formed a Grignard out of it. This was your compound given. So after this we formed a Grignard out of it. Then is Grignard का reaction we did with the oxidation product that is formed here as B. तो इन दोनों को react करा दिया. We reacted them together. After hydrolysis we got your final product. IUPAC naming of this matched it with our given answer. Overall a simple question, but if you actually had to check each and every option A, B, C, D, you'll go mad in the exam. It will take a lot of time. So be careful, be smart, be intelligent. Okay? I agree, advancement timing is not the factor, accuracy is, but we also have to keep our sanity in check. We cannot take 15, 20 minutes to solve one question. ठीक? चलिए आगे बढ़ते. Next. This is what all we covered. One of the classical questions and one of the standard issues that students face in advanced ka paper every year. Let's read the question. This is just an example, okay? I'm going to cover a concept using this. We have a alkyl halide given to us, and then NaI acetone, and we have alkenes forming. What is the logic used in this question? The logic that is getting used in this question is surely that these two bromines that we see, they will get substituted by iodine, and then when we have vicinal diiodide, so when we heat, it gives what? It gives alkene. E2 elimination takes place, and vicinal diiodide say we get alkene as the major product. That is what the question is targeting here. Okay? My idea is to try and make you understand how to conduct E2 elimination given a Fischer reagent, given the reactant as a Fischer projection formula. The logic is very simple. Whichever kind of Fischer is given to us, you simply convert it into a similar looking sawhorse. If this is your, let's say, carbon number P or carbon atom P, this is P. If this is your carbon atom Q, this is Q. Okay, whatever you see on the sides, put it on the side here. So that's pH and that's CH3. Here also you have H, you have Br. Whatever you see at the top and bottom, you put it directly. Nothing doing, no complex changing, no complex rotations. Whichever Fischer is given to you, just convert it into a sawhorse. If you remember, Fischer may anyways horizontal bonds are coming towards you. So these bonds are anyways coming towards you. See, pH, CH3, H and Br, they are coming, pH, CH3, H and Br, they are coming towards us, up, towards us as in from the back of the horse. So this we converted to sawhorse. Let me write it again for you here. This is your pH, this is CH3, this is H, this is Br, this is pH, this is Br. Now, in step 1, what is going to happen? Iodine is supposed to substitute Br, right? SN2 type reaction we have to conduct. We have to attack iodine and we have to substitute bromine. So let's do that first. On each carbon atom, ठीक है, वैसे भी कर सकते हैं. On each carbon atom, let's do the substitution first. So if I talk about this as the P carbon atom, inversion will take place, right? Inversion will take place. Iodine comes here, pH comes here, CH3 comes here. And then if we talk about the behind carbon atom, again inversion will take place. Iodine ends up coming here, and you will have H here and pH here. Okay, so as you can already see, we have two carbon atoms, both having iodine each. Now we just have to write this sawhorse in a better way, so that we can see elimination happening very easily. I here, pH here, CH3 here. The behind carbon I am just rotating so that you can see I opposite to each other. I repeat how to solve such questions. Here we had to do two things. We had to do SN2 and E2. So for SN2, if Br was present here, I attached iodine here and I flipped these. I changed these. Br was present here, I attached iodine here and I changed these. Okay, now I am rotating this so that both iodine comes exactly opposite to each other. When both iodine come exactly opposite to each other, these two iodines will get eliminated. And as you can see, this pH and this H are on the same side of this bond. है ना? So in the product also PH and H will be on same side of the bond on different carbons. So overall you can say कि two pHs are opposite to each other, are anti to each other. Complicated question, yes, but not difficult. Very scoring. Will definitely pull you from lower ranks to mid ranks at least. ठीक है? Whenever we do SN2 in a sawhorse, if bonds are like this, we simply make them like this. Meaning we just flip it. And when you have to eliminate, do E2 elimination, you have to try and bring both the eliminating group, both the groups to be eliminated opposite to each other. I hope this much is clear. Chalo. So that was a difficult question, that was a heavy question based on the substitution and elimination logic. Now, this is overall a simple question. Aromatic compound gives AgCl on boiling with alcoholic AgNO3 and one of the chlorine got substituted. Okay? Oh no, there are two parts. Compound gives AgCl on boiling with alcoholic AgNO3. यहाँ तक state part 1 and part 2 yields a C7H7OCl on treatment with NaOH. That means in this compound you have two chlorines but only one chlorine got substituted with NaOH. Let's try an option eliminate. ठीक है, आगे का question we will read, but let's try an option eliminate. He says compound A is, so compound A is supposed to react with only 1 mole of NaOH, not with 2. This part will not react with NaOH, this part will react, correct? So it's a possibility. This will not react, this will react, again a possibility. This will not react, this will react, again a possibility. यहाँ पे तो both the chlorines will react, so both will go away. This cannot be your A. Now he says A on oxidation gives a monochlorobenzoic product which can give only one nitro derivative. We know that whenever we have an alkyl group and we react it with alkaline KMNO4 or K2Cr2O7, the part circled here gets oxidized and converted to CO2H. So A option, the alkyl group on the top gets converted to CO2H. The group here remains as it is. Now let's look at the nitration options of this question. If we nitrate it, what are the options that we get? So CO2H is a -M -I group. Okay? It's a meta director. Cl is a +M -I group, although -M -I is strong. This is orthopara director, isn't it? So if we talk about CO2H, let me change the color. If we talk about CO2H, which is a meta director, CO2H would want that incoming nitro group comes to its meta position. If we talk about the Cl group, Cl is orthopara directing, para position is blocked, so Cl also wants it to come at the same position. Okay? That was about option A. Let's talk about option B. So in option A, it is clear that due to CO2H, due to Cl, both of them give mono nitro product. Both of them give only one position where we can attach NO2. Let's move ahead. So here you have CO2H, here you have Cl. This CO2H is a meta director. Oh, sorry. This CO2H is a meta director and we had Cl here. So CO2H meta director, that means this position due to CO2H. And if we talk about Cl here, Cl is orthopara director. So ortho and para. That means how many total possible products? Total possible products 4, isn't it? 4 different sites pe we are saying that we can get products. 1, 2. I'm not talking about which will give major, which will give minor. I'm saying that 4 different products are indeed possible. So this is not our answer. Let's move ahead. Let's look at option C finally. We have CO2H here, we have Cl here. Cl is a ortho para director. So that's ortho and para for you here. If this is CO2H in yellow, that is your meta director. Meta director say we get this and this. Please notice the 2 positions are not same. Although CO2H and Cl are pushing the incoming electrophile to the same position, to the marked positions, they are not identical positions. IUPAC nomenclature की वजह से, due to IUPAC nomenclature, if you put nitro at this A position and if you put nitro at this B position, both are 2 different products. But if you talk about compound A, यहाँ पे these 2 positions are identical. They are second position with respect to this carbon and they are first position with respect to the Cl carbon. Hence the answer here is option A. Very interesting, very good question here because we get confused in A and C. C maybe also we end up pushing the incoming electrophile to the same position where CO2H and Cl both are coinciding. But both the locations are different IUPAC wise and hence we cannot use it. ठीक? चलिए next question. Under identical conditions, solvolysis of which of the following substrate would lead to maximum racemization? In the last class we covered what undergoes racemization or which mechanism ka characteristic is racemization, that is SN1. More stable carbocation formed, faster is the rate of carbocation formation, lesser is the chance of a backside attack by SN2 and therefore more will be racemization percentage. More stable carbocation formed, more racemization percentage. Lesser stable carbocation formed, more inversion percentage. So basically the question is very simple now if you understand this. Ki out of the following 4, which gives most stable carbocation? In the first case, what do we have? We have this carbocation that has 3 alpha hydrogen. In the second case, we have a benzene ring with a withdrawing group attached, that's NO2, and we have a CH3. So we have a minus M group and we have plus H. M effect dominates over H effect. So overall this is a destabilized carbocation. Next, benzene ring, when no group is attached to benzene ring, what can it do? It can behave as plus M as well as minus M. So we use plus M, induced plus M effect of benzene ring and 3 alpha hydrogen here. So definitely this is much more stable. The C1 is much more stable than A and D. Last but not the least, we have a benzene ring जिसपे we have a OCH3 attached, CH, CH3 and we have a plus sign. OCH3 is a very strong plus M group and you have 3 alpha hydrogens का plus H as well. So guys, D या last वाले structure में, in the D structure we have most stabilization due to OMe group. ठीक है? So fourth or D will be the highest instability. Fourth or D will be the highest instability. After that we will have C because we have 2 stabilizing effects present here, methyl and CH3 ka. After that we will have A because it does not have any destabilizing, and then last B. Here dominating effect was minus M, here dominating effect was plus H. Here we had resonance along with plus H and here we had very strong plus M effect. So more stable carbocation formed, faster it will get formed and faster SN1 will take place in comparison to SN2. In every reaction, you will always have SN1, SN2 both competing with each other. If carbocation formed is very stable or more or largely stable, SN1 dominates. We covered this as a concept in our previous session. Please do watch the replay if you haven't. Chalo, next. This is perhaps the last question of the day, guys, but a very interesting one. The product of the reaction is just an alkene ether type system given. Heat, write the product. Goes complete bouncer. Unless you are able to relate it to Fry's rearrangement, you cannot even start the question. It doesn't even click what to do. Fry's rearrangement का question है, guys. We start working from this oxygen. CH2 double bond CH single bond O. Then you have your CH2 CH double bond CH2. Okay? So what happens here is these lone pair of oxygen initiate the reaction like this. Simple resonance. Now, because of high electronegativity of oxygen, this alkene is relatively electron deficient. See, this oxygen is applying plus M effect on this side, but is applying minus I effect on this side. So this side is electron rich, this side is electron deficient. So what we are trying to do, we are trying to attack an electron rich side onto an electron deficient side. This was your step 1, this was your step 2, 1, 2 are resonating steps. Step 3 is attack of del now minus on del plus. Step 4 is shifting of bond. Step 5 is breaking of this carbon oxygen bond. So if I have to draw the products out of it, we have CH2 here, we have single bond CH, we now have a double bond O here. This bond broke away, right? So there will be no linkage there. यहाँ पे we have CH2, then we have CH, then we have double bond CH2. Let's recheck if we made any mistake. No, there doesn't look like any mistake. One second. Yeah, there doesn't look like any mistake here. Oxygen attacked, pi bond shifted, pi bond attacked, shifted and out. Cool. So what seems to be our product? We seem to get C here as our final product. Fry's rearrangement. Basically this entire part breaks and attaches on the right side. I made a mistake in alkene. No, alkene is also. So this is your product here, guys, in Fry's rearrangement. That's C. Thank you so much, guys, for joining. And we end the reaction mechanism ka session here itself. We will continue ahead in from the next chapter, that is mole concept, and we'll discuss lots of questions there. Thank you so much for joining, guys. Take care. Bye bye.